In this video, you'll learn about how the free vibration problem is described and what we need to solve in this problem. You will then be provided with a review of complex numbers which are important for understanding where the proposed solution to the free vibration problem comes from. The free vibration problem. The free vibration problem simply analyzes the response of a dynamic system without any externally applied loads. Instead, only two initial conditions are prescribed. Firstly, the initial displacement, which we will denote as u at time 0, and 2, the initial velocity, u dot of 0. To analyse free vibration problems, consider the mass spring damper representation that we've been using. In this case, we have a rigid mass, which we denote by m, a single degree of freedom response, ut, a spring with stiffness k. But because this is an undamped problem, and because it's a free vibration problem, we do not have our externally applied load, and we do not have a dashpot. Recall that the equation of motion for a dynamic system is given by the inertial force plus the damping force plus the stiffness force, and this is equated to the externally applied load. Looking at our mass spring damper system above, we can see that we do not have a damping force and we do not have an externally applied load. So, for the free undamped vibration problem, this becomes the inertial force plus the stiffness, and that's equal to 0. This is a homogeneous ordinary differential equation. To analyse the free vibration response, we need to solve for ut. To solve equations of the form given in equation 2, we begin by making use of the exponential trial function. So, the trial function for solving equation 2 is given by ut equal to g times the exponential function st, where s is an unknown or a root which is to be determined, and g is an arbitrary complex constant. Before proceeding with this, we need to better understand complex numbers, which we have used to you in this and later sections of the course. The constant g used in equation 3 is a complex constant and has the form g equal to the real component, gr, plus I times by gi, which is the imaginary term. We denote the real component as re and the imaginary component as im. Geometrically, we can plot this on the imaginary and real axes. Where the x-axis is the real axis and the y-axis is the imaginary axis. We plot G as a vector which has a magnitude of G bar, an inclination of theta. Then, by geometry, we can see that the height of this, or the vertical component of this, is I GI, which is equal to I G bar sine of theta, and the horizontal component is GR, which is equal to G bar cosine theta. From this, we can then say that G is equal to G bar cosine theta plus I G bar sine theta. This can be expressed also in exponential form as G equal to G bar exponential I theta. Just note that I is equal to the square root of -1. For use in subsequent analysis, we need to derive some equations called Euler's equations. These allow us to move between different definitions of complex numbers. If we equate equation 5 with equation 6, we get G bar exponential I theta is equal to G bar cosine theta plus I G bar sine theta. If we then cancel out the G bars in this, then it's possible to say that the exponential function I theta is simply equal to cosine theta plus I sine theta. Or if we had the exponential of minus I theta, then it's equal to cosine theta minus I sine theta. These are what we call Euler's equations. And that these relate complex exponentials to their trigonometric components. You'll note that these are also simultaneous equations and that they may be solved to give cosine theta equal to half times by the exponential of I theta minus the exponential of minus I theta, and sine theta is equal to 1 over 2i times by the exponential of I theta minus the exponential of minus I theta. These results will be used extensively throughout this part of the course.